Hello and welcome to the new session on fluid mechanics. As we were discussing about the numerical problems in the previous class, the problems that were dealing with the force exerted by the flowing fluid on pipe bends, will have 3 to 4 more problems related to same topic before we head to the new topics in the same module. Take down the next problem. A pipe of 300 millimeter diameter conveying 0.3 meter cube per second of water, 0.3 meter cube per second of water has a right angled bend, in a horizontal pipe, full stop. Find the resultant force, exerted on the bend, comma, if the pressure at inlet and outlet, of the bend is 24.525 Newton per centimeter square and 23.544 Newton per centimeter square. Okay. If you look at this problem, the two problems that we have solved related to pipe bends, one was a 45-degree bend. This was the 45-degree bend, and then you had a 135-degree bend. Now it is exactly 90 degrees in the horizontal pipe. This is the horizontal pipe and this is the right angle bend. Of all the bends, right angled bends are relatively easier when asked to find out force exerted by flowing fluid on the pipe bend. I will let you know why. Now looking at the data, we will have to draw the exact representation of the diagram, that is the pipe bend. Now it is a 90-degree pipe bend. What is the diameter of the pipe? It is not a reducing bend. The pipe is carrying a discharge of 0.3 meter cube per second, and the diameter of the pipe is given to be 0.3 meters. I will draw the diagram according to the given data. It is a 90-degree bend in a pipe which is having 0.3 meter diameter. As I have told you, first we will have to draw the center line of the pipe. That means this is exactly 90 degrees. So if you know how I usually wrote all these things, this is Fx, this is Fy. Now 0.3 meter is the diameter of the pipe and no reducing bend, so it remains as it is. The diameter even after the bend will remain as it is. So this becomes section 1 and this section 2. Please remember, though I show section 2 here, that section 2 lies here only. That is very important point, because whenever we apply Bernoulli's equation, if at all there is a need, then we will have to know that section 2 is here but represented here for clarity. Now the pressure on this point P1 is given, and if I am not wrong, it is equal to 24.525 Newton per centimeter square, and pressure on section 2 P2 is nothing but equal to 23.544 Newton per centimeter square, and the velocity at inlet is in positive x direction and is equal to V1, and at section 2 velocity is moving in the upward direction. Velocity is in the upward direction, that I have shown as V2. Why I mentioned that the problems on right angled bends are easier? Because at section 2 you have no component of horizontal, and in inlet you do not have component of vertical. That reduces the burden. So I need not have to draw those two diagrams that I used to write. accompanying the problems. If you remember the 45-degree bend and 135-degree bend, I wrote two additional diagrams. Why I wrote them? Because the pressure at outlet, that is P2, and when you multiply it by the area corresponding, it became P2A2, was neither horizontal nor vertical, but I wanted the components of those P2A2 in both horizontal and vertical directions. Whereas in this case, you do not have to worry about it because P2A2 is actually in vertical direction. So, if you write the data sets given, you have diameter of the pipe being equal to, in fact I will write this as D1 is equal to D2 is equal to 0.3 meters. Therefore, A1 is equal to A2 is equal to pi by 4 D square, that is pi by 4 into 0.3 whole square, which comes to be 0.07, that is 0.3 square into pi by 180, sorry, pi by 4. So, 0.0707 meter square, and then you have P1 and P2, which I have already shown in the diagram. Additionally, you have been given discharge. What is the advantage of having discharge? Once you know area and discharge, you can calculate what is the velocity. So, you have V1 equal to V2 equal to Q by A. That means 0.3 divided by area is 0.0707. That gives you 4.2433 meter per second. So, now when you apply impulse momentum equation to the entire setup, what do we know from impulse momentum equation? First in x direction and then in y direction. Impulse momentum, so I will write it, applying impulse momentum equation first in x direction. In x direction, how do we apply? What are the forces in x direction? Now you have the first force, that is P1 A1 in the horizontal direction. So, I will write it as P1 A1, and when you reach this point, you have Fx in the positive x direction, but for the equilibrium, the pipe bend would be exerting some force on the flowing fluid. So, I will take it as negative Fx, and in the vertical direction you have P2A2, that means nothing in horizontal direction. So, I will just simply represent it as 0. This must be equal to rate of change of momentum. How do I represent rate of change of momentum? Rho q into change in velocity. So, rho q, which represents mass, multiplied by change in velocity, that is final velocity minus initial velocity. What is final velocity in horizontal direction? Final velocity is in vertical direction, that means in horizontal direction final velocity is 0 minus initial velocity in x direction, that is V1. So, if you just substitute, you will get the answer. Now, what is P1 A1? P1 is 24.525 into 10 power 4, because it was given in Newton per centimeter square, multiplied by A, that is 0.0707. This is P1 A1 minus Fx. This must be equal to rho. He says water is flowing in the pipe, that means rho is 1000 into Q, discharge he has given 0.3 into 0 as it is minus V1. How much is V1? 4.2433. When you solve this for Fx, you have keep Fx to the right hand side, send everything onto the other side. So, 24.525 into 10 power 4 multiplied by 0.0707, and when you send the entire thing to that side, it becomes positive. So, plus 1000 into 0.3 into 4.2433. The solution is 18612.165 Newton. Similarly, when you do for y direction, now if you put impulse momentum equation for y direction, take everything in y direction. Now observe, do you have anything in y direction at inlet? See, P1 A1 is in the exact horizontal direction, so no component in y direction. I will simply write 0. And moving ahead, you have Fy. Fy is in the upward direction. For me, upward is positive. So Fy, for me Fy in the upward direction is negative, downward positive for me, upward negative. That's how I have taken in the previous problem. Stick to one thing which will not lead to any confusions. Fy is in the upward direction, so minus Fy. And in the vertical direction, you have P2A2 in the exactly vertical downward direction, so plus P2A2. This must be equal to change in momentum. So rate of change of momentum is nothing but mass per second into change in velocity. Mass per second is rho q into change in velocity. Final velocity minus initial velocity. Final velocity in y direction is in the upward direction. For me, upward is negative. So minus v2 minus initial velocity in y direction is 0 because v1 is in the pure horizontal direction. It has no components in y direction. So when you do this, minus Fy, keep that to one side. Remaining things you can send it to the other side, or keep Fy, send Fy onto the right hand side, keep rest of the things to this side. What am I left with? Fy is equal to, what is P2A2? P2A2 is 23.544 into 10 power 4 into area is 0.0707. 0.0707 minus. So when you have sent this to the left hand side, negative would have become positive. So I will write it as positive. Rho is 1000 into Q is 0.3 into V2 is 4.2433. Be careful, we have been using rho g in pressure measurement unit. If you remember module 1 chapter 2, we have extensively used rho g. Students have a tendency to forget what we have written here, though they themselves would have written rho q. In the next step, instead of q, they would take 9.81. It spoils the entire problem. Please don't do it. It is rho q, which is mass by time. So now when I solve this, you have 23.544 into 10 power 4 multiplied by 0.0707 plus 1000 into 0.3 into 4.2433. That fetches you an answer of 17,918.598 Newton. Now you have Fx and Fy. When you have Fx and Fy, it is easier to find out the resultant force. We know that resultant force F is equal to root of Fx square plus Fy square. What is Fx square? 18612.165 square plus 17918.598 square whole under square root. That gives me an answer of 25,835.805 Newton. This is the resultant force. I can as well calculate the direction of this resultant force using alpha is equal to tan inverse of Fy by Fx in modulus. So I have Fy as 17918.598 divided by Fx, that is 18612.165, and tan inverse of the answer will give me 43.91 degrees. So how do I represent this? With a neat diagram. Both Fx and Fy here are positive. Be careful, in the previous problem Fx was positive, Fy was negative. Now both are positive, that means Fx and Fy are to be shown like this. Fx in the positive x direction, Fy in the upward direction, and with the horizontal resultant F makes an angle of alpha. This is the representation. That is why I said the job of solving the problem related to 90-degree bend is easier, and also in this problem no need to find out the pressure at the outlet, so that means you need not apply Bernoulli's equation also. So now this completes all sorts of problems on pipe bend. We are still left with problems on nozzles that we will take up right now. It is slightly different but based on the same concept. Take the next problem. A nozzle of 20 millimeter diameter, a nozzle of 20 millimeter diameter is fitted to a pipe, of 40 millimeter diameter. Full stop. Find the force exerted by nozzle on water. Find the force exerted by nozzle on water which is flowing through the pipe at a rate of 1.2 meter cube per minute. Okay. Have you ever seen a nozzle? If you have not seen the nozzle, it is very simple. You will definitely have it in your houses attached to the taps. Since the tap water is not uniformly coming out, you will always put a nozzle to it so that the flow is regulated and you have it in the perfect line. Now, the same nozzle is fitted to a pipe. So now what is happening, because the diameter of the nozzle is smaller than the diameter of the pipe, there is a tapering section. Flow is continuous obviously. Then what do we have to do with the problems on pipe bend now? Why is the problem on nozzle categorized under force exerted by flowing fluid on pipe bend is because when there is a tapering section, obviously the pipe diameter is changing though the flow is continuous. Of course, since the flow is continuous, you can apply continuity equation as well. You can apply Bernoulli's equation. Now, what does the momentum equation say? It is based on, you very well know that momentum equation is definitely a part of law of conservation of mass. So, in that case, when the flow is taking place in the pipe to which the nozzle is fitted, you can always apply impulse momentum equation and find the solution. Now, what is given to me? It is a pipe of diameter 40 millimeter to which a nozzle of diameter 20 millimeter is attached. As usual, I will draw the center line of the pipe. And now, a 40 millimeter pipe is attached with a nozzle which is 20 millimeter in diameter. So, this is that tapering section. So, now take the section 1 here, and after the nozzle you take section 2. Now, the pressure at section 1 is P1, area of section 1 is A1. See, P1 is not known to me. A1 can be calculated because diameter at section 1 D1 is equal to 40 millimeter means 0.04 meters. Get me A1. Now again section 2 you have diameter of 20 millimeter. 20 millimeter means 0.02 meter. You can solve for A2. And here please be careful here. Pressure at section 2 is very, very important. This is a pipe. I have taken section 1 here on the pipe which has started somewhere else. I do not know where pipe has begun. Now I have only considered a part before there is transition. So this is a continuous pipe. The flow has some pressure here, that is what I have taken as P1. Whereas when you come to section 2, where nozzle is fitted to the pipe, nozzle is the discharging part. That means the water from here flows to the atmosphere. That means this nozzle is open to atmosphere. So pressure at section 2, P2, is nothing but equal to P atmospheric, which is considered as 0 in all our measurements. So P2 is negligible, or P2 is atmospheric pressure, you can consider it to be 0. The velocity of flow here is V1. The velocity of flow here is V2. Now why I have written all these things is, using P2 you can find out P1. How do I do that? It is based on application of Bernoulli's equation between section 1 and section 2. What do I actually have when I apply Bernoulli's equation? At this section 1 and section 2, the total energy must be same. That means P1 by rho g plus V1 square by 2g plus Z1 must be equal to P2 by rho g plus V2 square by 2g plus Z2. It is visible that Z1 and Z2 are equal. P2 is known and is equal to 0. P1 is unknown. Then what are the things that are to be known? V1 and V2. How do I calculate V1 and V2? I can calculate that only when I have area and discharge. Has the discharge been given in the problem? Let me check. Yes, it is given as 1.2 meter cube per minute. Q is equal to 1.2 meter cube per minute. It's a special case. Always you will have meter cube per second for discharge. Now it is given as meter cube per minute. How do I convert? 1.2 meter cube divided by 1 minute is 60 seconds. Therefore Q is equal to 1.2 divided by 60, which is nothing but equal to 0.02 meter cube per second. Now I will have to calculate the area. 0.04 square multiplied by pi by 4. This fetches me an answer of 1.2566 into 10 power minus 3 meter square, and A2 0.02 square multiplied by pi by 4. This fetches me an answer of 3.1416 into 10 power minus 3 meter square. Why I found them here is, I need to know what is V1 and V2. Here only I will calculate. V1 is nothing but Q by A1. So it is nothing but 0.02, which is Q, divided by A1 is 1.2566 into 10 power minus 3. That fetches you an answer of 15.9159 meter per second. Once I get V1, similarly V2 must be equal to Q by A2. Q is 0.02 divided by A2 is 3.1416 into 10 power minus 4. That means you have V2 to be equal to 63.6618 meter per second. Again you can cross verify why V2 is greater than V1. V1 is the velocity of flow in the pipe, which has a higher diameter, whereas V2 is the velocity of flow in the nozzle, which has a lower diameter. That means when the area is decreased, velocity automatically increases, and that is reflecting in the calculation of V1 and V2. Now you need to know what actually is the pressure force at section 1, because pressure force at section 2 is known and is equal to 0. Why is it equal to 0? Because pressure at this section is nothing but water is going out to the atmosphere. That means the section 2 or nozzle is open to atmosphere, and hence it is under atmospheric pressure, which is taken as 0. So P2 is 0. Now what actually is required? In the problem he has mentioned a very catchy word. He says find out the force exerted by nozzle on water. Compare this statement with the 3 previous problems we have solved. In all the 3 problems we have solved previously, he has asked us to find out the force exerted by flowing fluid on pipe bend. Now it is the reverse case. he has asked you to find out the force exerted by nozzle on flowing fluid or nozzle on water. Nothing will change except you will find minus Fx in place of Fx. That's the only thing that you will be finding out. The same equation can be applied here. If you observe, the fluid will be flowing in this direction, but whereas you will have the force exerted by the nozzle on the flowing fluid in the negative direction, which you will always take as minus Fx. So, and also here the flow is in the horizontal direction alone, and hence you need not have to apply impulse momentum equation in y direction. It is sufficient if you find out if you apply the impulse momentum equation in x direction. To do so, you will have to apply Bernoulli's equation first. So, applying Bernoulli's equation, you have P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. You very well know that the center line of both pipe and nozzle are at the same level. So, Z1 and Z2 gets cancelled. P2 is nothing but atmospheric pressure considered as 0. So, that also gets cancelled. So, what are you left with? P1 by rho g, that is unknown. P1 is unknown, divided by rho is 1000 into g is 9.81. This must be equal to V2 square by 2g minus V1 square by 2g. What is V2 square? 63.6618 square divided by 2 into 9.81 minus V1 square by 2g. What is V1? 15.9159 square. V1 square is 15.9159 square divided by 2 into 9.81. Now, to find P1, you have 63.6618 square minus 15.9159 square whole divided by 2 into 9.81, and this must be multiplied by 1000 into 9.81, that is sending this denominator onto the right hand side. You will get a value equal to 1899754.453 Newton per meter square. Remember, this is pressure. Unit for pressure is Newton per meter square or Pascal. Once you get P1, the next step would be to apply impulse momentum equation. So, apply, because now I have everything required, P1, P2, A1, A2, V1, V2 and Q. So, apply impulse momentum equation. Only available direction here is x direction, because flow is only in x direction. So, how do we apply impulse momentum in x direction? So, pressure force at section 1 or at the inlet is P1 A1 and minus Fx. What is minus Fx? That is here. Fx is the force exerted by flowing fluid on the nozzle, whereas nozzle is exerting some force equivalent to that on the water. That is why I have taken Fx with a negative sign, minus Fx, and you have P2A2 in the negative direction being equal to 0. This must be equal to rho q into final velocity is V2, that is also in the positive x direction. So, I have taken V2 minus initial velocity in x direction is V1. So, what is P1? You have just found out. So, if you send all these to, so I will write as it is, no worries, 1899754.453 into area at section 1 is 1.2566 into 10 power minus 3 minus Fx is equal to rho q. Rho is 1000 into g is q is 0.02 meter cube per second into V2. What is final velocity? 63.6618 minus initial velocity is 15.9159. As I have told you, you are finding out the force exerted by flowing fluid. You are not finding out the force exerted by flowing fluid on nozzle, but you are finding out the force exerted by nozzle on flowing fluid. So, keep minus Fx as it is, send rest of the things to the other side. So, you will get 63.6618 minus 15.9159 multiplied by 1000 into 0.02. So you will get this value 954.918 minus this entire thing, that is 1899754.453 into 1.2566 into 10 power minus 3. So that gives you a value minus 1432.3134 Newton. The negative sign indicates that you have found out the force exerted by nozzle on flowing fluid. This is the solution we were looking for. You may add the line at the bottom. Negative sign indicates force exerted by nozzle on flowing fluid. Take down the next problem. You can solve it as homework based on the problem that we have just solved. Diameter of a pipe gradually reduces from 1 meter to 0.7 meter. 1 meter to 0.7 meter. Full stop. The pressure intensity at the center of 1 meter section, is 7.148 kilonewton per meter square. And rate of flow of water through the pipe is 600 liter per second or 600 LPS. Full stop. Find the intensity of pressure. At the center of 0.7 meter section. 0.7 meter section. Full stop. Also determine the force exerted by flowing water on transition of pipe. Read the last line of the problem. He says force exerted by flowing water on transition of the pipe. You underline that. That means this is to find out positive effects. And go to the previous problem and underline that the force exerted by nozzle on water, which signifies that you are finding out minus effects, that is force exerted by nozzle on water. Now how do you solve these problems? I will give you a few hints. It is very similar to this problem. Assume that this is 1 meter section and there is a gradual transition and later it is 0.7 meter section. You have to be very careful. It is not the nozzle fitted here. That means section 2 is not open to atmosphere. That means this also is a part of continuous pipe. That means P1 and P2 are to be found out. That means again you will have to apply Bernoulli's equation, for which he has given you pressure at inlet, that is P1 is given. To find out P2 you can apply Bernoulli's equation and get P2 as well. Once you get P2, again apply impulse momentum equation in x direction, you will get what is Fx. So that completes the problems related to application of Bernoulli's equation, modified Bernoulli's equation, and as well you have completed the problems on force exerted by flowing fluid and pipe bends. And in the next chapter of this module, that is second chapter of third module, you will study about the application of Bernoulli's equation. Thanks for patient listening. Good day.